Hello, my name is Kwang-Young Shin from the Virtual Machine and Optimization Lab in Seoul National University. I will present our work Progressive Training of GANs by Prioritizing High-Level Features. First, I will briefly introduce the background and motivation of this work. Generative Adversarial Network, or GAN, is a framework that trains a network called generator to create fake realistic data when given a real dataset. A separate network called discriminator is trained to distinguish the fake generated data from real ones and is used to train the generator. This training process is known to be brittle, especially if the resolution of the data, images in this case, is high. Many works were proposed to stabilize GAN training. One of the proposed methods is to guide training by prioritizing global large-scale concepts. It is based on the intuition that complex tasks are better done in steps, learning large-scale global concepts first and then local, detail-specific concepts later. The nature of convolutional networks means such high-level features are processed by layers that process low-resolution feature maps. This is because convolutional layers has limited receptive field, so only when the resolution of the feature maps are low can it effectively process high-level features that are large-scale and contain global concepts that can affect the entire image. As such, works that prioritize global large-scale concepts focus on layers that process low-resolution features. For convenience, I will refer to such layers as low-resolution layers from now on. StackGAN and ProGAN are one of the first GANs that successfully trained high-resolution images. StackGAN utilizes additional discriminators specialized for low-resolution images, and it uses those additional discriminators to train the low-resolution layers of the generator. ProGAN initially trains on very low 4x4 resolution images, and then progressively doubles the resolution by introducing higher resolution layers until the highest resolution images can be trained. Such works train on low resolution images as a means to train global large-scale concepts. However, lowering image resolution can lead to information, which is not desirable. There are also many complications that arise when supporting low-resolution image training. StackGAN has to support multiple resolution training and utilizes separate discriminator networks for each resolution. The generator also has to be able to generate multiple resolutions of the fake image data. ProGAN modifies the network architecture in training time and utilizes smooth transition techniques to gradually modify the architecture. Both methods incur significant overhead that can prevent widespread adoption. The motivation of this work is, can we prioritize the training of high-level features without lowering image resolution or modifying architecture? Since high-level features are processed by low-resolution layers, we interpret it as whether we can prioritize training of low-resolution layers without relying on low-resolution image or architectural modifications. We propose to prioritize low-resolution layer training by simply training them more frequently. This means having the gradients applied more frequently compared to other layers. I will call the proposed method selective layer update for the rest of this presentation. First, only the lowest resolution layers are prioritized and are updated most frequently. This is because since the resolution is lowest, it is considered to process the most global, most large-scale concepts. Next, the subsequent highest resolution, the next higher resolution, that is the second lowest resolution layers, are included into the list of prioritized layers. This inclusion of the subsequent higher resolution layers is repeated until all layers are included into the list of prioritized layers. This leads to progressive training of lowest to highest resolution layers, such training of the most global concepts first, and then to the most detail specific, most fine detail specific concepts last. It is performed on both the generator and discriminator. The following is a concept diagram of the proposed method. In the first stage, layers that process the lowest resolution features are updated more frequently compared to other layers. The update frequency of the prioritized layers compared to the other layers is represented by the hyperparameter R. Prioritized layers are updated R times from R different mini batches, and then the other layers are updated once. This is repeated until the next stage. In the next stage, the next lowest resolution layers are also prioritized and updated more frequently compared to the remaining higher resolution layers. This continues until the final stage, where all layers are considered as prioritized and training proceeds as a typical GAN training. When updating prioritized layers, the other non-prioritized layers are not updated. Similarly, when updating the non-prioritized layers, the prioritized layers are not updated. We found that not doing so can occasionally introduce training instability. The implementation was done on the publicly released program code, which we found very helpful. The full resolution flicker phases high quality dataset was used to train the networks, using one GPU with a mini batch size of 4. The Wasserstein loss with gradient penalty and atom optimizer was used. Other techniques, except for the progressive growing technique, were kept the same. For the proposed method, the stage length per stage was determined by manually inspecting when the improvement in FID starts to flatten. This graph compares the proposed method with the naive method, which doesn't have any techniques to prioritize high-level features. The naive method simply trains the full network like a typical GAN. The proposed selective layer update method has a slow initial improvement in FID, but surpasses naive around 3000 kilo images. The stage length for the first stage is 100 kilo images, and then for the next 3 stages is 300 kilo images, and then for the remaining 4 stages it is 700 kilo images. and after the 3,800 kilo images trained, training proceeds as if it was as a typical GAN. Next, we compare the proposed method with naive and the program method with respect to training time. The improvement of the proposed method over naive is more pronounced because the proposed method can skip calculation of high resolution layer gradients in the initial stages. This means it can train a larger amount of killer images given an equal amount of time. However, it can be seen ProGAN trains faster and achieves better final FID than both the proposed and naive method. In conclusion, the proposed method of training low resolution layers more frequently to initially prioritize high-level features can improve GAN training. It is a simple method that does not require in-training time modification of architecture or support for multiple resolution images. It trains from start to end on the highest resolution image only. For future work, we plan to find improvements so that it matches or exceeds the performance of ProGAN, and to test it on more complicated architectures such as StyleGAN 2. This is the end of my presentation. Thank you for listening.